Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Great. Okay, so now we're going to hear from Harry Berman on position-based cryptography.
Thank you. First of all, I want to, nevertheless, thank you for inviting me and allowing me to speak here and being part of the summit. It was a wonderful experience. And indeed, I do want to talk a bit about position-based quantum cryptography. But while preparing my talk, I thought it would be more interesting to take a step back and sort of have a more general theme. So the real title is going to be the 2 applications of port-based teleportation. Before that, I have to say that I'm from Amsterdam, where we already started doing quantum computing 20 years ago in '95. And by now we have about 10 people working on computer science aspects of quantum computing. And we work on the area of algorithms and also no-go theorems. Communication complexity was one of the themes that was developed partially in Amsterdam. Quantum cryptography. Another nice one is quantum proofs, where you use quantum mechanical ideas to prove classical statements, and this has proven to be extremely successful. And last but certainly not least, few qubit applications, which is a general theme of this meeting as well. And so today I will touch upon these 3 areas. So, but first of all, let me tell you what is port-based teleportation. Do you all know what port-based teleportation is? Or someone doesn't know? Very good. I hope so. Because everyone knows what teleportation is. And in teleportation, the goal is to send an unknown state, psi, to the other side. And the 2 parties, Alice and Bob, usually they share an EPR pair. And what happens is that Alice prepares, does a measurement, a Bell measurement, which has as outcome 2 classical bits. And those bits can be sent then to the other side, where if you do the Pauli correction on the other half of the EPR pair, you have in your hands the state psi. And so this is all very well known and a basic building block of quantum information. Now, port-based teleportation is a Japanese invention. I'm not going to pronounce these names, but the idea is the task is exactly the same. So again, you want to move over psi to the other side, and you have EPR pairs at your disposal to do that. But unlike normal teleportation, you have many EPR pairs now. And again, a measurement is done much more complicated than the measurement here for teleportation on one side, on Alice's side, and the outcome of that measurement is a number I. And the I ranges, points to one of these EPR pairs. We have n EPR pairs, and this number I that comes out of this measurement points to one of these ports, they're called. And it now happens that if you look at the other side, at the ith end of the port, the state psi has appeared there. So note that this is somehow different than normal teleportation, because you don't have to do this correction at the end. But you still have to know where to collect your state psi from. So there's no correction. Actually, it's also not perfect, so there's a little error. It may fail, so this measurement may fail. But for the rest of the talk, just imagine that this is the primitive, and actually you can make this error very small by just having more EPR pairs. Good point. So let's compare, it'll come now. So let's compare, if I want to teleport an n qubit state to the other side, it will cost me n EPR pairs, and 2n classical bits. Now if I want to do that with port-based teleportation, it will require 2 to the n EPR pairs.
How complicated
And,
is the measurement?
well,
Can we do it?
that's one of my questions. So I think it would be very interesting to have an experiment doing small port-based teleportation scheme. But we can talk about how complicated it is. And so in my talk, so I thought it would be nice to have these two applications of port-based teleportation. The first one is to quantum position-based cryptography, which will take most of my talk. And then the second, if I get there, but I may have been over-enthusiastic in thinking what I could cover in 40 minutes, I will show how to use port-based teleportation to generate things that are called non-local games or Bell inequalities from communication complexity protocols. So hopefully I get there. But the first part of the talk is on position-based quantum cryptography, and that is done together with these guys. And the idea is the following. So in '69, man landed on the moon, or so we think, because there are actually a staggering, I think it's 29% of Americans that actually think that that never happened and that it was staged somewhere in Hollywood, and there was nobody ever leaving the Earth atmosphere. And so the goal in position-based cryptography or in position verification is to actually prove that you were or that you are at a certain location in space. So can you prove without any doubt, unlike the doubt that we have for man landing on the moon, that you are at a certain location in space? For example, this could be very useful because you know then, for example, that the launch missile command really comes from the Pentagon, or that you're really talking to South Korea and not North Korea. And another one is the pizza delivery problem, where your neighbor tries to play a prank on you and orders 50 pizzas for you. And then when you open the door, you get these 50 pizzas, but you never ordered them. So clearly, the pizza company needs to have a position verification scheme in place. Moreover, when you have this position verification, you can use it as a building block for other cryptographic tasks like authentication and position-based key exchange, which leads to the nice primitive that you can send a message to a certain location and you can only read the message when you are at that specific location. Okay, so position verification really should be thought in a three-dimensional sphere or a three-dimensional world. But for the purpose of this talk, I'm going to the one dimension, the line, because all the problems already are present there, and it's much easier to reason about. So let me put it on a little bit more rigid setting. So here we have our line, and we have on either side, we have two verifiers, which I've called verifier 0 and verifier 1. And somewhere in between the two verifiers, not necessarily in the middle, there is a prover who claims that he is at a particular position. So this is like the man on the moon. And what I assume for now is that there is communication that's going to occur between the verifiers and the provers, and that communication occurs at the speed of light, not faster and also not slower. Moreover, I assume that the machines on these locations have infinite computation power, so they can instantaneously compute. Of course, that's also not true. And I'm also assuming that these two verifiers are allowed to coordinate beforehand, so they can share entanglement and they can share a protocol. And so what does it mean for a protocol to be secure? Well, it is secure if there is no coalition of fake provers that pretends towards the verifiers that there is someone at the claimed location. So in pictures, it means that there cannot be two fake provers. In this case, Alice and Bob are the bad guys, such that they intercept messages and somehow pretend towards the two verifiers that there is someone in the middle, whereas there is nobody. So that's what you want to shield against. So let's try a classical scheme from the 90s. It's called distance bounding, and it works as follows. So time flows from top to bottom. And now imagine that the verifier sends a string X to the prover, to the claimed location, and the prover, upon receiving it, immediately returns this message back to the verifier. And of course, when you time how long that takes, that gives you, because of the speed of light assumption, that gives you an upper bound on how far away the prover is from the verifier. Now, the other verifier could do the same thing and also time it, and that also gives you an upper bound. And these two cones intersect in precisely one position, and that's where the prover sits. And it seems that this is a secure scheme. But it isn't, because we have to now see whether there can be an Alice and a Bob that fake the whole thing. And there can be, because what Alice can do is the following. She can intercept this X when it passes by here, and she stores it, and she waits a certain amount of time, the same amount of time that it would have taken the X to go this message to go to the blue spot and go back, and then once it is here, she sends it back to the verifier, and the same thing Bob does, and so from the point of the verifiers, it appears as if there is someone at the blue spot, but there isn't. So this scheme is not secure. So let's try something a little bit more complicated, because it wasn't really used that these two X and Y's, that the X and Y were somehow together at some point. So let's ask from the prover to compute some function, some function that depends both on X and Y, and that outputs A and B. And it quickly computes that, and then sends along A and B back to the verifiers and times everything. And if everything times out okay, then this person is at the claimed location. But unfortunately, this can also be broken, and it can be broken as follows. Again, Alice intercepts this message X, and not only does she keep a local copy, she also sends on X to Bob. Right? So she makes a copy of the message and keeps the copy at home and sends on the rest to Bob. Bob, of course, does the same thing. And now look, at this point in time, both Alice and Bob have X and Y at their disposal, so they can compute quickly f of xy, which is A and B, and then send on the A and B to the verifiers. And everything looks as if there was someone at the blue spot, but there wasn't. There were this Alice and Bob faking that position. And basically, this was in 2009, the proof that classically you cannot have position verification. You can always perform an attack, you can always fake it in this sense. Okay, so it will be useful to think about this problem as a game, which I call the attack game, which is the following. We have our Alice and Bob, and what they're trying to do is they get as input X and Y, and they have to compute f of xy, and they are allowed to send to each other one message. Right? This was this copying and send on procedure. And then after receiving the messages from each other, and these messages have to be sent independent of each other. Right? It's not that Alice can wait till she receives Bob's message and then prepare her message. She has to send them simultaneously. And then at the end of the day, she has to output A, and Bob has to output B. And as we saw, that was perfectly possible in the classical setting, because these messages were X and Y. But now, if we want to perform a quantum version of this, there's quite some hope, because this copying of the input, if that's a quantum information, then it cannot be copied. And so maybe there's a scheme lurking in the background that allows us to do this nevertheless in a quantum way. And indeed, some quantum protocols were devised. Here's one, where we have a random qubit being sent by the verifier, and the prover, upon receiving this qubit and upon receiving a bit that is sent by the other verifier to the prover, upon receiving both items, the state and the bit, the prover, either if the bit is 1, sends it on to the verifier, and if it's 0, he sends it on to the other verifier, and then the verifier checks, the one that received the qubit checks that it was the qubit that was supposed to be sent. So let's study how Alice and Bob can fake this. Well, Alice and Bob are allowed to send each other a message, and without loss of generality, you may assume that Bob just sent his classical input, because that's all that he has. And Alice has to prepare somehow a state depending on her input state, and she may keep some qubits at home and sends on some qubits to Bob. And note that if the bit is 1, so then Bob has to output the qubit that Alice received. And that means that Bob is able, from the message that he receives from Alice and the fact that B is 1, to produce this state. On the other hand, if the bit is 0, then Alice has to be able to, upon knowing that this bit is 0, be able to produce from the stuff that she left at home, that she somehow that's left over from this state, produce psi as well. And if you look at this a little bit, you see that this is copying of information and that this is not possible, right? Because you can pretend that Alice got a 0 and let her produce psi, and you pretend that Bob had a 1 and let him produce psi at this point in time. And indeed, this was a proof that this was impossible, and so it seems that we have a quantum protocol that is secure. But actually, what these people forgot, or well, they thought about it, but they thought it wasn't necessary, was that Alice and Bob actually can share some entanglement. And when they do, then you can actually break this scheme. And here's how you break it. It's kind of cute. So we have Alice who has psi and Bob who has this bit B. And what Alice does is she performs teleportation, so they share these two EPR pairs. And what Alice does is she performs teleportation, unaware of what the bit is, and teleports her qubit to Bob, which you can think of a encrypted version of the state that really was there, and the encryption key is in the hands of Alice. And what she does is she sends on these two bits, C1 and C2. Now Bob, who knows that the bit is 1, and he knows that he has to output the qubit in this case, he can just, upon receiving this C1 and C2, he can just perform the decryption step of teleportation and output the state psi. So if this is what they do, and B is 1, they're perfectly fine. But what happens when B is 0? Well, Alice, unaware, of course, that the fact that B is 0 does the same thing as she did before, so she teleports and sends on these bits, C1 and C2. And Bob, who now knows that he is not the one who has to output the qubit, but Alice has to be it, he just teleports back this qubit to Alice. And Alice now has this doubly encrypted qubit on her side. And then, when they've done this, they send to each other their keys and the fact that the bit is 0. And now Alice, who knows now that she has to output the qubit, she can first undo the teleportation error introduced by Bob to get back her own state. And of course, because she knows how to undo her own teleportation error, because that was classical information and that she could have copied, she can undo it again and produce psi. So this works, and it's kind of a bit counterintuitive, but it works.
It doesn't take extra time?
So this is all. So this teleportation step is really instantaneous. So I'm telling it as if it's a story, but really it is like one push at the button and it's instantaneous. So then more complicated schemes were thought of and actually also broken until we in 2010 showed that there is a general no-go theorem for even in the quantum case. So even quantumly you can break any scheme. And actually Gilles Brassard had a nice item in this, in Nature News and Views. And so what is the most general scheme? Well, it is something like this. The verifier 0 sends some quantum state, and the verifier 1 sends some quantum state. And the prover has to perform some unitary transformation on both these two quantum states, do some measurement or whatever, and send on two quantum states, tau A and tau B, that may be entangled. Right? This is the most general scheme that a quantum that you can dream up in the quantum world. And so the attacking game is as follows. So we now do allow Alice and Bob entanglement, and they receive this row A and row B. They are allowed to send each other a quantum message, and then at the end of the day, they have to produce tau A and tau B. And what we showed was, using ideas from Weidmann, that you can actually, very much along the lines of this back and forth teleportation, perform this task as given here. Although we needed unrealistic amounts of entanglement. We needed a double exponential amount of entanglement in the size of the of the number of qubits. And then shortly after, there was a very nice improvement by Beggi and Koenig, who showed that you can get by with only an exponential amount of entanglement. And what they used was this port-based teleportation. So I will tell you how that works, and that is immediately the first application that I wanted to share with you. So here is the task again. We have this this row A, and what Alice does in the first step, and again this is instantaneous, so I'm telling it as a story, but it really happens instantaneous. She first teleports this row A system to Bob, who somehow receives now on his end of the EPR pairs a scrambled version, an encrypted version of the state row A. And this outcome of the Bell measurements, which will be a bunch now, Alice records. And now Bob, who now in his hands has this encrypted version of row A and the input row B, he now port teleports, using many EPR pairs, he port teleports this system back to Alice. And of course there's a port I, which is the true port that contains this state. Of course, Alice is unaware of which port is the right one, but she does know that there is a port, namely the ith one, where if she first undoes the error on the A part and then applies the unitary that they have to apply on the whole thing, will give both tau A and tau B. So she does that on all of these ports, not knowing which one is the right one, and that will produce a whole bunch of tau A's and tau B's. And she keeps the tau A's at home and sends the tau B's to Bob. And note that the ith one here really contains the right tau A, B. And so Bob, so now here's the information, the messages that are sent. Bob sends I to Alice, and Alice sends all the B parts, the tau B parts, to Bob. And now when they know that I is the right port, Alice can output tau IA, and Bob can output tau IB. So this is, in one shot, how you can use both teleportation and port teleportation to break this or to solve this game. So it shows that there is a no-go theorem and that you can get by with a single exponential amount of entanglement. But a very natural question, I think also a very important question, is this optimal? Do we need really an exponential amount of entanglement, or can you do it with much less? And in particular, and I think this is very interesting, can you come up with a protocol in this port-based teleportation where the attack requires a lot of entanglement, but the honest prover and verifiers are efficient, and they don't need a lot of qubits? So that's what I have been looking at recently. And here is a single qubit protocol based upon ideas of Kent, Munro, and Spiller. And the idea is the following, and we have been trying to implement this. But first let me tell you what the scheme is. At play is 1 qubit, psi, which is encoded either in the +1 basis or in the 0-1 basis or in the ± basis. And this is sent to the prover, and also a classical string y is sent to the prover, and a classical string x. It sort of combines all the ideas you have seen so far. And what the prover does upon receiving all these items, he first computes a function f of xy, right, because he has x at his disposal and y. And this f of xy will tell him in which basis to measure the qubit. And once he knows what basis to measure the qubit in, he can report the outcome to both verifiers. So this is a nice scheme, and provided that this function f is easy to compute, it's also easy to implement this because only 1 qubit is at play, and it's prepared in some easy basis that can be measured easily. It's very analogous to the BB84 protocol. So how does the attacking game for Alice and Bob work? Well, Alice and Bob are allowed to send each other a message, and then they have to give back the outcome of the measurement of the fxy measurement to this input.
Sorry, what is the function exactly? Is that
so that's something that you can design yourself. Yeah, you can choose it. And if you want this to be a practical scheme, it has to be a function that you can compute efficiently. Otherwise, it would not work. And so, an interesting question that we actually don't know really how to solve is show a bound on the amount of entanglement that you need for functions like this. So these functions are labeled by this function f that you have to design yourself. And for each function f, there is a minimum amount of entanglement that is needed to solve this game. And I want to study this notion ESQPF. And we don't know how to do that. That's kind of a difficult, deep question. But what we could prove is that if you assume that the Alice and Bob don't have any entanglement, which actually is a fairly reasonable assumption these days, Alice and Bob don't have entanglement, then you can show that it is secure. And we hope actually to prove that that it actually requires an exponential amount of entanglement to break for easy computable f's, but that we couldn't prove. But it has the nice property that you can implement it using only one qubit. So we went to talk to the group of Nicolas Gisin and Hugo Swinden in Geneva, who actually performs these BB84 protocols, and we asked them, can you please implement this for us? This sounds like a cool thing. And then immediately all kinds of problems popped up from doing experiments. First of all, and I didn't know this, but this is of course well known for the physicist, if you shoot photons through fiber, it doesn't run at the speed of light, but it runs slower. It runs at 2/3 the speed of light. So that was a bummer, because for our timings, we needed that. But actually, that turns out to be not a problem, because you can time it in such a way that first you send the slow qubit to the prover, and then when it arrives at the right location, you send, well, slightly before that, you send your x and your y at the speed of light, because those are classical, and those you can actually send at the speed of light. So this turned out to be something that could be overcome. But then they had another nasty surprise for us, and that is the following. If I send a photon through fiber, it will arrive always. There's no doubt about it. If I send something, it will arrive at the other side. But what the Gisin group told me is, no. If you send 100 photons, then maybe one will arrive. Certainly if your distance is large enough. So that was another bummer, because it turns out, and I will show you, that if you have these losses of photons, then our scheme becomes immediately insecure. It's very much like the detector efficiency for Bell inequalities. And here's how that works. Because this function, right, that was 1 bit. And now what Alice can do, right, and sometimes these photons don't arrive. So the classical scheme also has to have the possibility of saying, I didn't receive anything, I'm not playing this time. And so what Alice does upon receiving her input x and the state psi, she just guesses the outcome of the measurement. So she guesses the outcome of f of x, y, and measures psi in that basis, and sends on a, x, and z to the other side. So she sends on what she guessed, she sends on what her input was, and she sends on what the output was of her measurement. And Bob sends just his y on to Alice. And now, when they both have received this information, they both know, they can compute whether the guess of Alice, the initial guess, was correct. And if that guess was not correct, they say, no, don't play, I didn't receive the photon. And if it was correct, well, then it was correct, and then they play as if they received it. So with just 1 out of 2 photon loss, they can fault this scheme. So that's not good, because actually only 1 out of 100 photons arrive. So we changed our scheme a little bit more to, instead of having 1 basis, have a whole bunch of bases to code in. So instead of having your photon in 0 and 1 and this sort of the in-between one, you sort of have this almost continuous possibility of bases in which you can code your photon. And actually they can do this in the lab, so that was fine. And so more information now is needed. So both x and y together, say the sum of them modulo k, code which basis the qubit is coded in, and then this is the scheme, and then once they receive that, they measure in that basis and produce the outcome. So this is a slightly more complicated scheme, and we were able to also show that for this particular scheme and the realistic values of errors that occur in the protocol and these photon losses, it still is secure. So this is sort of something that hopefully will be implemented soon, and that then shows as proof of principle that when you don't have entanglement, you can have position verification. Actually, I'm not going to reach my second part, unfortunately. But so concluding, quantum position verification is something that is impossible unconditionally, even in the quantum case. But it's very interesting to come up with a restricted set of schemes that are very easy to implement, even on nowadays, on technology that we have nowadays. And we can prove that it is secure when you don't have entanglement. And by working a little bit along these lines and coming up with somewhat more complicated schemes, we hope to get better security parameters. In particular, I think it's still very possible that you have a scheme where you prove that where you only need 1 qubit in the honest case, but you need an exponential amount of qubits in EPR pairs to break it. And that will be, of course, a perfectly secure scheme for all practical purposes, because we will not have 2 to the 100 EPR pairs. Okay, I guess 240 was where I should stop. So.
I started a little late.
Okay, well, shall I maybe quickly say something about the other part, which is a completely different topic, but it's kind of nice as well. And so, first of all, do you know what communication complexity is? Well, so you want to solve this problem. We have basically seen it, f of xy, and you want to minimize the amount of communication. So let me skip over that. Also, quantumly, you can do that. Non-locality, non-local games is a similar thing, but there's no communication. It's like communication complexity without communication. So Alice and Bob, they share a state, they get an input, perform some measurement on that state, and produce an output. And then you can look at the correlations that are given by this conditional probability distribution that arise from quantum protocols, and you can look at the probability distributions that arise from classical schemes, where they have not EPR pairs, but they have shared randomness. And in order to somehow quantify these two scenarios, you define a game matrix, or I call it a game matrix, or a Bell inequality that tells you, given input x and y and output a and b, was that a good output or was that a bad output? And a good output is positive and a bad output is negative. And when you do that, somehow you score the runs of this protocol, and you score the ones that are good, and you negatively score the ones that are bad. And you can tweak this gx, y, ab. And when you write down the value of this game, it's somehow an average over all inputs x, y, and outputs a, b, and you compare how well you scored with in relationship with this game matrix, and there's also some input probability on your x and y. So, but don't worry too much. Think of omega star as the quantum value of this game. How well can you play it quantumly? And omega g is how well can you play it classically. And traditionally, these two things have been compared, and ratios thereof have been looked at. So you basically will look at the ratio of how well can you play the game quantumly and how well can you play it classically. And somehow optimal violations are known. I mean, you can give bounds on them, but actually no explicit game is known in the literature. I mean, we don't know an explicit game that gets everything optimal. So it's an open problem to come up with a constructive game that violates all parameters. And actually, I think it's interesting to have these non-local games, because they in turn can be used to verify quantum systems, and they're also used in this device-independent cryptography. So these are, apart from being interesting from a physical point of view, they can actually be used in quantum computation and quantum cryptography. And so this is something that I've been thinking about for a long time. How can we use quantum communication complexity protocols to get Bell inequalities? And if you have an advantage quantumly, how can you get an advantage in this Bell inequality setting? And here's how it goes. So let's assume we have a one-way protocol, a one-round protocol, where Alice sends k qubits to Bob. They have their x and their y. And Bob has to output the value f of xy, and he does so by using his y to do a measurement on the qubits that he received from Alice, and that is the value of f of xy that they need to do. And now assume that the probability that he is correct is 1/2 plus epsilon, and assume furthermore that no classical scheme can achieve this. So for any k-bit classical protocol, the success probability is much smaller than 1/2 plus delta. Right? So quantumly you can do fairly well, classically you cannot do very well. So delta is much smaller than epsilon. So how are we going to use this protocol to build a non-local game? And here is how it goes. So here are the k qubits of Alice. And what she does is she port teleports now this state to Bob. And so this was the second application of port-based teleportation. And she outputs I. And I'm describing here a run of a protocol, and then I'm going to tell you what the correlations were that were good. And Bob, he of course doesn't know what I is, so he performs the measurement belonging to his input to all of the ports. So he produces a long list of 2 to the k values, b1 up to b2 to the k, and the ith one will actually be equal to f of xy. And this is precisely the correlations of the game. It's fairly easy. So the game matrix on xy and outcome I and list b is 1 if and only if the ith one really is the value f of xy, and it's -1 if the ith one is not f of xy. And so this gives you a game matrix, and you can now fairly easily see that if you could play these correlations classically, so if you were able to produce these correlations classically, then that would induce a one-round classical protocol that only used k bits to compute f of xy. And why is that? Because what Alice just does, she generates this I classically and sends it on to Bob. And that is just log of 2 to the k, and that's just k bits of information. So this sort of port-based teleportation allows you to produce a non-local game that cannot be won classically. So if you work it out, you see that the quantum value of the game is at least epsilon, and the classical value is at most delta. It's when you do it like this, it's really this bias, how much more than 1/2 you win. And so you get this nice ratio. And actually, let me quickly go through this. I mean, of course, you want to do this for multi-rounds, and then there's a problem. But we solved it, so I'm not going to bother you with what the problem is, but I'm telling you that we solved it. And here's the final slide. So if you have a multi-round protocol for which there's a quantum advantage over a classical advantage, then you can get a violation of Bell inequalities. And there's a little bit of a loss. So if it's an R-round protocol, we require that the classical protocol is even bad when it has R times K bits of communication. So now you can apply it to all kinds of communication games where there is a big advantage. And so that's what we did. Yeah, so we did get some new Bell inequalities that got almost optimal violations, so that's nice. But the drawback is that it actually required a lot of entanglement again. So remember, this port-based teleportation used a lot of entanglement. Well, that sort of is killing us on this side. But in theory, this gives you a general method to produce a Bell inequality from a quantum protocol. And that's where I want to stop.
Great, let's think. Other questions?
Yeah, I'll go. So with the experiment, I'm kind of curious. Since you're going in fiber, are you using time bit encoding for the photons?
No, just polarization.
Okay, cool. So then the next question about time-bending coding. Have you considered taking a look at that? Because it sounds like it could be very interesting because the quantum data, the operations now are kind of having spread over the time axis. So the timings could be affected by what Alice and Bob are doing.
Yes. So we did think of time binning, and we already had a nice scheme where you had like multiple bins, and you got some nice interference, and then the experimentalists, Gizin and Hugo looked at me and they said, "We're not going to do this interferometer with these long arms." And I did that for my thesis, and I'm not going to do that again. So you're right. It gives you much more possibilities because you can have more inputs. But they said no. But maybe we have to push harder.
Question about the position-based protocols. You mentioned there's a choice of function for which the honest parties just require one EPR pair, and dishonest parties require an exponential number.
Correct. Yeah. Well, the honest one actually is not even a EPR pair.
Not even a EPR.
One qubit.
Right. But that seems very non-graceful the way this degrades in terms of the position, right? You wanna basically lie about your position. You need an exponential number. But if I just want to lie a little bit, it's like I want to do a little fib about my location. Then I also need to spend an exponential amount, or does it degrade somehow with the position I'm trying to lie about?
Well, I mean, let's assume that you still have infinite. I mean, because if your computation takes a while, it's really like a little bit of an epsilon ball around the thing. But say, suppose that you're outside of that ball, yes, then you would require exponential. Well, we didn't prove it, but then it doesn't really matter where you are.
Okay, even an epsilon away from the true location, I immediately have to spend an exponential.
Yeah, because then you need two parties, and timing-wise, if they're sort of far away,
right,
then they don't have enough time to send each other stuff. They require this entanglement.
Okay.
Yeah.
Okay, thanks.
By analogy, if at night you may not distinguish a bush from a person, but if a person moves, it's much easier to distinguish.
And it's not a bush, usually.
Right.
Or you had too much to drink, yeah.
So, if your prover is not standing still, but moves.
Good question. Yeah. So then it's again a different scenario, and so we assume that you are in the White House and you're not moving to another location in Washington.
So that may break. I don't know.
But you're right. That's something else. But then, what would you prove that I? I mean,
if constantly you monitor the location of that, and then maybe also at the known time you happen to be on the moon.
Yeah.
And then
well, I mean, the moon. Right? Imagine where these verifiers have to sit. They have to sit even around the moon, right? But
even people in Amsterdam will believe.
But moving around is indeed something to look at.
Similarly, the relativistic limit would be very interesting.
Yeah.
So you see.
Great. Well, let's thank Harry again. And then